Okay, this is Chapter 6, Part 1 of our video series, and Chapter 6 is about momentum. So we've talked about Newton's first law as a statement of inertia, and we know that something that's more massive takes more effort to get going than something that's less massive. So now what we're going to do is introduce speed into that mix. The more massive something is, the harder it's going to be to stop. The example I use on the slide is a kayak and a cargo ship. The kayak would be much easier to stop than a cargo ship if they were going at the same speed. So that new addition of speed is our concept that's known as momentum, when we're taking the mass as well as how fast the object is moving. So we have what we call linear momentum. It is a product of the mass times velocity. So you can see we have a new symbol, which is lowercase p, and that equals mv, mass times velocity. If you notice, our units are kilograms times meters per second. So we get our kilograms from our mass, we get our meters per second from our velocity. So if you have any other kind of units, you have to convert. If you're given mass in grams, if you're given speed in kilometers per hour, miles per hour, you need to convert to get the units of kilograms, meters per second. It's important to note that it is a vector quantity, and it's going to point in the same direction as your velocity vector. With that being said, if it's a vector quantity, we can decompose it into x and y components, as you see by the picture in the lower right. So just like our velocity, momentum is going to be positive if that particle's moving up and to the right of the x-axis, or if it's on the y-axis, or it would be negative if it's moving to the left or down. So let's look at this problem we have. We're asked which has the greater momentum, an 18-wheeler parked at a curb or a Volkswagen rolling down the hill. Well, first let's think, what has the more mass? Well, your 18-wheeler is going to be more massive than your Volkswagen, but notice your 18-wheeler is parked, so your 18-wheeler has a zero velocity, whereas your Volkswagen is moving, so it has a velocity. So the one that's going to have the greatest momentum is actually going to be your Volkswagen, because you're multiplying that mass times that velocity. Now let's look at a problem. Remember, we want to start our problems with our list. So you're running north at 3 meters per second. So your velocity is 3 meters per second. You have a mass of 80 kilograms, and you're asked to find your momentum. We know that our momentum is mass times velocity. So our momentum, our mass is 80 kilograms, and our velocity is 3 meters per second. So our momentum is going to be 240 kilograms meters per second. And because we're running to the north, it would also be to the north because it's in the same direction. Another problem we have is, suppose you're in a 800 kilogram race car. So let's say the mass of the car is 800 kilograms. You're going 200 miles per hour. So your velocity is 200 miles per hour. You have a mass, so we're going to say MP for mass of the person is 60 kilograms, and you want to know what's the momentum. Well, you're in the car, so therefore the total mass is going to be the 800 kilograms plus the 60 kilograms. So the total mass is going to be 860 kilograms. Now we know momentum has to have the units kilograms meters per second, but we're given our velocity in miles per hour. So that tells us right there that we have to convert. So we look on our conversion table and we see that in 1 mile we have 5,280 feet. We see in 1 meter we have 3.28 feet. In 1 hour we have 60 minutes. And in 1 minute we have 60 seconds. So our velocity is going to be 89.4 meters per second. And let's just double check our units. So hours cancel here, miles cancel here, feet cancel here, minutes cancel here, and we're left with meters per second. So we did it right. So then your momentum is going to be the mass times velocity. Our total mass is 860 kilograms times 89.4 meters per second. So our total momentum is going to be 7.7 times 10 to the 4th kilograms meters per second. Okay, so we know that momentum is going to change if velocity and or its mass changes. So this expression right here is Newton's second law. Now Newton realized mass or velocity could change. So remember that acceleration is the change in velocity over the change in time. So because we know mass and or velocity can change, we can rewrite Newton's second law onto this format. Okay, basically the delta is the change, so we're saying it can change mass. We know that acceleration is the change in velocity, so our acceleration is represented here by delta v over delta t. Now, if we take that equation that we just looked at, and we had that our net force equals delta mv over delta t, and we want to solve it for the change in momentum, all we did was multiply delta t by both sides. These cancel, and you can see how we got to this relationship. The interaction that changes an object's momentum is your force that acts for a certain time interval. And momentum is now represented by a capital J. Okay? So your momentum is net force times time, but notice it's also delta mv. Okay? It is a vector quantity, and it has the same direction as the net force. Okay, this ends part 1 of chapter 6.